So it gives me great pleasure to introduce the annual Distinguished Lecture in Computer Science here at Churchill College for 2024. We have had a number of distinguished speakers over the years, famous computer scientists, famous academics, famous industrialists, people who have done startups. The distinguished lecturer today is one of our own. Tim Harris was an undergraduate and a grad student at Churchill. He was a grad student, I just ascertained 5 years after I was. I did my PhD from 92 to 94, and he started in 97. We ran into each other occasionally as youngsters in the Eagle back in the good old days. And Tim then became a lecturer at the Computer Lab and a Fellow of Churchill, a Title A Fellow. He then took a different path in his career and went to work in industrial research. And I thought it would be interesting to invite Tim to give this distinguished lecture, because this is perhaps a more typical trajectory for Churchill computer scientists than becoming academics. We've got a huge ecosystem of research and development labs and tech companies in Cambridge in which many of our alumni make careers. And now Tim has been going great guns at this for a couple of decades now, and so he can tell us what it's like, what it's about, what sort of fun you can have, and what sort of things you can achieve. Tim, over to you.
Great, thank you, Russ. And thank you for the invitation to come back to Churchill and speak here. I've lived in Cambridge pretty much since I started as an undergraduate. And I was realizing just now that there's only probably a handful of times that I've taken the opportunity to come back to college. So thank you again for the good excuse to come here this evening. So what I'm going to talk about is some of the different things that I've worked on over the years in the course of my time here. Start very briefly with kind of when I first got involved with computing back in I think it was the 80s, it may even have been the late 1970s. I grew up with computers around the house back from the time when my father was working with early computers in UK space science. So this, I think, was me with an Amstrad CPC computer. I was always involved in trying to make things run fast and efficiently. This was a program that I worked on when I was at secondary school. It was some software to plot these so-called fractal pictures, computed by iterating a mathematical formula and picking a color based on how many times the formula executed before a certain boundary condition was reached. I was doing mathematics and doing computing at secondary school and thinking about what to do next, and have here the prospectus as it was at the time that I still found I had a copy of. And I realized that I could combine a visit from Plymouth, where I was growing up, with coming to Churchill College and coming to the computer lab on the same day. So that was one of the criteria for making the long journey. I picked Churchill because it was same day, open day. I also picked Churchill because there was a director of studies in the subject here, Frank King, who is here in the audience, and I remember from my undergraduate admissions interview. And then as a tie-break, Churchill came first alphabetically out of the colleges that met those two criteria. So for whatever reasons, good or bad, that worked out well for me. I arrived as an undergraduate in 94. I graduated with maybe a more ill-advised hairdo in 1997. And during my time as an undergraduate, I took the opportunity to have summer jobs at a range of different companies. I'll talk about one of them a little bit more in a moment. But what really attracted me was the work I saw going on in the systems research group in the computer lab. This is one prominent project from the time, an operating system called Nemesis, which was an early system designed for playing digital audio and video. And this was the kind of time where if you took a lot of care over how you organized the computer software, you could play audio and video on a desktop computer. Now, this is something which is kind of taken for granted now because the resources of the computer are so good that it just works straightforwardly. But at the time, this was something where you could get it working instead of not working by designing the operating system with some carefully thought through principles. I joined that team and worked on a PhD thesis on aspects of running the Java virtual machine on Nemesis. And as part of that, I had the opportunity to spend an internship at Sun Microsystems with the team that developed Java. And I'm going to talk about some of the work that we did as part of that as well today. I came back from the internship, and that was really at the peak of the dot-com boom era of early 2000. I think this is a graph from the NASDAQ stock price hitting a peak almost literally on the day I finished my internship. What it meant for me, though, was that there were many people in the computer lab out running startups and exploring opportunities there. And I was able to get a position teaching, covering initially for my former PhD advisor's course on computer systems modeling. I went on to work on broader systems research topics and designing programming abstractions for multiprocessor machines. I'll touch on some of these examples some more. I did that for about 4 or 5 years, but then subsequently moved on to a series of industrial positions, some in research and some in product companies focused on topics which, if we were publishing about them, could have been published, but we were really driven by the goals of getting these big systems working. So I'll give a few examples of projects I worked on with Microsoft, the research lab here, for about 8 years. A couple of things I worked on with Oracle, running a small research lab in Cambridge. After that, I spent a couple of years with Amazon Web Services, and then came back to Microsoft just at the start of the pandemic, working with a more distributed team on AI workloads. I'll finish with an example of those. So I've gone through these different phases in my work in computer science and in my career. I'm going to organize the examples today in terms of the developments that have happened in computer hardware over that same interval. So going from single processor systems, desktop systems, maybe not even networked, through to the kind of large-scale cloud distributed systems and the GPU systems that underpin a lot of AI workloads today. I've got one example from each of these. I'm going to focus on some of the techniques we've used in projects to make systems run fast and run efficiently in each of these different settings, and how those requirements have changed over the years, reflecting the evolution of the devices. So this first example is going back to a problem that we were set when I started as an intern at a company called Bullfrog Productions, a computer games company. And at the time, I was working on what became part of the, I think it was called Dungeon Keeper game. And this problem was set to people who started as interns as a kind of check that people know how to program once they arrive before they're let loose on something more substantial. And the problem is a kind of simple logic game. We've got 12 pieces, each of them 5 squares per piece. We've got the full set of pieces. These are all the ways you can have 5 squares tiled together like this. And we've got to put them into a board of 6 by 10 squares. So each of the pieces gets used exactly once. We're allowed to flip them around, rotate them, and so on. And we want to come up with solutions like this. And we want to, as part of this problem specifically, to count the number of such solutions that exist. The number is still etched in my mind. It's 2,339 solutions to this problem. And actually, finding a single solution here is an NP-complete problem. So many approaches to this are going to effectively come down to a brute force search of how we can take these pieces and organize them into the grid. And I had a go last weekend at re-implementing this problem and to see just what the performance was like on a modern machine. And the starting point for the brute force approach could be to pick one of the tiles, put it in the top left corner of the grid, and then to proceed by figuring out, well, for the next tile, we've got to maybe do some flipping and rotating to get it to mesh in correctly here. And then we'll work either fitting tile by tile or filling space by space with each of the possibilities that we see. I wrote a simple version of that, and running on a reasonably modern machine, with 12 nested loops trying to place each tile in turn. I started it running, I went and cooked and ate dinner, and it had not found a single solution. So it kind of, as you might expect for a brute force searching problem, it's not running quickly. The insights that we had here when thinking about this problem and how to get it to run in a reasonable time on the machine is, instead of thinking about these tiles and shifting and rotating and all of these transformations we can do, we can represent this board as a bitmap. We can exploit the fact it's got 60 squares, so it'll fit in a single 64-bit value in a current machine. We can also represent each piece as a bitmap, just showing 1 where the piece has a square present and 0 where the piece has a square absent. And we can then just do logical AND to test, does this piece fit in the grid at a given point? We can also pre-compute all of the possible shiftings and rotatings that we do for these pieces. So we're not having to redo this every time as we're shuffling pieces around and trying to fit them together. And we can have a trick to avoid needing to do double counting due to symmetry of flipping everything by picking one of the pieces and saying, well, we're not going to flip that one individual piece. So what we do then to try to build this is to say, well, let's organize the work on a tile-by-tile basis in the underlying 6x10 grid. So we'll form a list for the first square of all of the possible ways we can shift and rotate the shapes, with that first square being the first square in that shape that we've got non-empty. And we'll do the same for the second square. And here I'm just looking at this C shape. In practice, we do it for all 12 shapes. And we come up with a list of all of these different shiftings and rotations that are valid. We get, in fact, only, it surprised me, it's kind of only 1,800 different possibilities here. So when we get rid of the cases where tiles are hitting and going over the edges or off the bottom, then we get about 1,800 different possibilities. We can compute all of those and get a 64-bit value bitmap for each of those possibilities, compute that ahead of time in a fraction of a second. And then as we're trying to solve the problem, what we do is we work square by square along the grid, just thinking about it as this 60-bit bitmap now. We pick the first empty square that we've got in the grid. We then go down that list of different tiles we can fit into that first square. And we just do a logical AND to check, is this tile going to fit in that square, given all of the other squares we've already placed? If it fits, we take it out of this list that we maintain of the shapes we've not yet used, and we move on to the next empty square in the bitmap here. So we've still got something that is a brute force solution here. We've not done anything particularly clever in terms of algorithms, and this is still an NP-complete problem that we're looking at. But we've now got a way of expressing that problem that maps very well to the computer hardware. The inner loop of finding solutions is about 5 lines long. All it's doing is logical AND operations and iterating down arrays. So all operations that are implemented very, very quickly in the processor. And also, we've got that array I mentioned of pre-computed options for each of the shapes. It's only about 16 kilobytes. So it fits in the level 1 data cache of the processor, so the fastest possible access we've got to data there. There's some other tricks that we could do on newer machines as well. But even without doing those tricks and just looking at this basic mapping that links well to the hardware, we're able to get performance where instead of going away for dinner and coming back and not finding any solution, we can compute all of the solutions within about 15 seconds. I suspect if we applied these other techniques, splitting the work across multiple cores in the system, using some of the new SIMD instructions that have been introduced over the years, we could probably get this down to 2 or 3 seconds for finding all of the solutions. So this is really the recurring theme of the examples I'm going to talk about, that if we're looking at how to get something to perform well on a given machine, we need to understand these kind of details about what the hardware provides with us and how to map the software that we're designing down onto things like the size of the level 1 data cache and the instructions that the hardware is giving for in this case, the bitwise operations for testing. And this can make a huge difference from something that is impractical to run on a given machine to something that is very straightforward to try. And it's a direction that's come back to me many times over my career, trying to identify cases like this where we can shift something that is a problem where you might have to start a test running, go away several days until you get the results, down to something where we can leave something going either interactively or at least run a set of experiments overnight and come back to a new set of data to analyze the next morning. So we'll go on to the next example, which is looking at shared memory systems as opposed to that single machine, single processor system that I started out with. And this was the kind of hardware that was typical around the time I was finishing up as an undergraduate. I think I spent some of the money I earned working at Bullfrog Productions on a computer system with 2 processors in it, something like these 2 Intel Pentium Pro in the example. But by the time I started an internship during my PhD, we were thinking about machines like this one on the right-hand side. The machine there is a system, I think, a Sunfire system from Sun Microsystems, and it could have up to 106 processors in the machine. These processors themselves would often be supporting multiple threads. They'd be used in software that's running multiple threads internally. And rather than just thinking about these 2 processors and how the operating system might distribute work across them, maybe running 2 different processors, one on each at the same time, and using classical abstractions like semaphores, mutexes, condition variables. Here we'd often be thinking about running one process on the entire machine with multiple threads and thinking about how those threads can communicate most efficiently. For example, how the memory that they access as they're running is located physically inside the machine, where the threads that synchronize on the same memory are going to be located. These kind of questions. And these kind of physical questions are very significant here. If we think about the speed of light, about a foot per second, then that means that in a machine, this rack-size system, then we're looking at counting in terms of processor clock cycles the time it takes just for that speed of light propagation in the system, even before we think about all the other costs that are involved. And this overlapped with the emergence of Java as a programming language. So that both added a more imperative to getting parallel software to work well, as well as more opportunities for a broader set of developers to be writing concurrent systems, given the features that Java provided for concurrency in the language itself. So if we think about those kind of systems that were emerging, there was a big soup of different instructions that were proposed as ways for threads to synchronize with one another within the machine. So just like in the Pentominoes example, I was thinking about, well, how do we best use the bitwise operators we've had in classical single processor systems? We've now got this big set of different operations. And we've got to think, well, first of all, as someone designing a system, what operations should the hardware provide? And then as someone building software, how best do we make use of those to make the software run as effectively as possible, to make as good use as we can of the big expensive hardware that we've just got? There's a very nice example on that first question, which is some foundational work from a colleague when I was at Sun Microsystems, Maurice Herlihy. And he observed how, in a particular technical sense, this compare and swap instruction is what we need. Now, we cannot build compare and swap out of these other building blocks, so it's more expressive than they are. And conversely, using compare and swap, we can build anything else in a kind of particular framework for describing concurrent algorithms. So that work was very influential in showing that compare and swap was a good choice for hardware designers to be providing, rather than some of these earlier alternatives or esoteric kind of ideas like having queues built into the hardware. The work that I was doing, kind of along with Maurice and others in the group then, was looking at how to build on compare and swap and to make scalable data structures. Now, the example that I'll talk about here is kind of almost the simplest data structure that we can think about, a linked list. And using a linked list to represent a set with insert, lookup, and delete operations on the set. And in order to benefit from the hardware, we're going to design this linked list so that we build it without using locks. So there's some more precise formal ways that this ought to be defined. But just informally, here I'm thinking about building the set by going directly to the memory instructions read, write, and compare and swap, as opposed to using the kind of techniques that we talk about in the actual concurrent systems course of building locks and then using those locks to synchronize access to shared memory. So this kind of idea has got a lot of popularity. It's often seen as a way to make software faster and scalable. It has other benefits, though. It avoids threads impeding one another's progress in the way that would happen if we used a lock and we had one thread holding a mutual exclusion lock that some other thread needs. Here we're saying, well, let's put some more constraints on the programmer. We won't use locking in building our concurrent system, and we will tackle this more ambitious problem in order to try to give better performance and scaling to the users of the system. Now, one of the things that we realized quite quickly when thinking about building data structures without using locks is that many operations almost work if you take out the concurrency control. And it's one of the reasons why informally concurrency control bugs are hard to find, because often we can take the concurrency control out and many executions work still. So let's think about what happens if we have a set represented here by a linked list, and we have a thread that is walking down the list looking for some particular value. So it's looking for 20. It looks at here, it's got 10. Okay, so it's not found 20 in this linked list. We then get to 30, so now it kind of knows that the 20 ought to have been here, and the lookup for 20 ought to return false. We then have another thread that's working on that exact same linked list, and we're not using any locking, remember, so there's nothing preventing these two threads running together. And this thread is going to insert 20. And again, it can do this just using that single compare and swap instruction. It finds where its new 20 ought to go. It's going to go just before the 30. It creates the 20 in its own memory, and then it starts doing this atomic compare and swap to compare the pointer from the 10 to the 30 and to replace it with a pointer from the 10 to the new 20. And what happens here is that because we're doing that compare and swap atomically, because that's what the hardware is giving us, we're able to arbitrate between multiple threads all trying to do things on that same location, and only one of them is going to succeed in what it's doing. And we're atomically checking that we have the state we want and updating it to the state we want to establish. Now let's look what happens if we do lookup and insert together. So without any locking, we've got that same example. The 20 lookup is going down the list. We do the insert, running all of those steps as before, kind of sneaking in behind the back of the lookup of 20. And we've then got this situation. We've got one thread working on the list is tried to find 20 and it's not found it. And another thread has tried to insert 20 and it succeeded in inserting it. So that raises the question about whether this is correct or not. You know, we've got these two operations doing conflicting things, giving these set of results. And is this a correct version of a set? How do we think about more complicated mixes of operations rather than this initial example? And there's an idea which Maurice Herlihy co-developed, which helps us answer that problem. And that is to look at the behavior of the threads interacting with the data structure, the linked list here, and to look at a trace of what they're doing. So the thread doing the lookup is kind of going along in real time left to right. The thread doing the insert is running quickly in the middle. And the lookup finishes its work here. And we say that this is a correct behavior for the linked list to have if we can identify points inside each of these intervals when it looks like the operation ran atomically. So the justification for this being correct behavior is to say that in the actual observations that we could make from these threads, we don't really care about the interleaving of the individual instructions. All we care about is that we've seen the lookup run first here and the insert run second here. So from an external observer's point of view, we can't distinguish what's happened with our carefully designed lock-free set using compare and swap from a set that was using just atomic operations, running the entire operations both atomically. So let's have a look now at what we can do if we want to add deletion to the set. And this is the piece that along with colleagues I was working on during the internship. And this is tantalizing because it almost works again if we use atomic compare and swap. You know, we are going to try and delete 10 out of the list here. We're going to update a single pointer to do the deletion, so that's succeeded. But we don't have the correct behavior any longer when we have a mix of operations on the list. We could have one thread that's trying to do an insert of 20, that other thread doing the deletion of 10, and we end up with two threads both doing compare and swap, both succeeding because they're doing their comparisons on two different locations. And so there's nothing that forces these threads to communicate in any way and leads them to discover that they've got this kind of tangled mess with the new node getting cut out of the list at the same instant that it's inserted. And the technique we developed to let us keep these good lock-free progress properties at the same time as building a correct list was to realize that we could exploit some knowledge of the details of the hardware again. And in particular, in machines at this point, all of these pointers would be pointing to an aligned location in memory. So we would typically have the address of each of these objects be starting on an 8-byte boundary, and that would mean that the addresses themselves had 2 or 3 bits that would always be 0 at the bottom of them. So we could find purposes to use these bits while still maintaining the integrity of the list by ignoring the values we stuff in those bits while traversing it. And in particular, we could use a bit to indicate that a node is one that we want to delete from the list. So we're using this a little bit like a tombstone in a hash table. We're going to set this bit to indicate that we want to delete the 10 node, and we're then going to have one compare and swap doing that kind of bit set, and then a second compare and swap cutting the node out of the list. We sometimes call this logical deletion, adding this tombstone versus physical deletion, tidying up the list. And what this means now is that we've induced a conflict in the memory system between the thread doing the deletion, setting the tombstone bit, and the thread doing the insertion. So out of those two conflicting updates, we've now induced a conflict in the memory system, and whichever thread runs first will do its operation, and the thread that runs second will notice the interference and restart the work that it wanted to do. So this was kind of surprising as we were working on this. Right? This is going back about 20-something years at this point. And even then, it was surprising that we could publish a research paper about the implementation of basic features in a linked list. And I think with some hindsight, one of the reasons for that is that as the computer hardware has evolved, each of these different steps, there's opportunities to revisit the design and implementation choices, even of fundamental data structures like this. And because we were working on this just as the emergence of these large multiprocessor machines, there were opportunities to identify new techniques that have lived on in some of the standard libraries in Java and elsewhere since then. So another example where knowing details of the hardware, like the availability of these spare bits, and thinking about the interaction with the processor's caches, we can design an algorithm that runs quickly and performs well. I'll skip on a few more years now, and we look at the next generation of large multiprocessor systems. And here we're kind of physically, we've got the same rack size individual machines. But we're now looking at a machine where instead of having just 106 processors in the system, we've got maybe 4,000 hardware threads all running concurrently in that one machine. This particular system was a Spark M716, so it's got 16 physical processor sockets. Each of those processor sockets here has, I think, 32 processor cores, and each of the cores has 8 hardware threads supported internally. So if I'm getting the numbers right, it multiplies up to 4096. So this was a machine that was running different kinds of workloads to the ones that originally motivated that 106 processor system. And the kind of example we've focused on while thinking about software for these machines were in-memory analytics workloads, particularly things like graph analytics or large-scale data analytics. And trying to design this software so that we could put all of the data that we're querying inside memory, and we could then answer complex queries in an interactive style, in the kind of timescale that a user would be looking for responses. Maybe they're investigating something and want to be forming a hypothesis, doing a query, getting results that will help inform their next query. And these machines were providing an opportunity to do that, given the large physical memory capacity they had and the large processing capabilities. Just as an illustration of these algorithms, one that we focused on a lot was PageRank. And this is the same kind of PageRank algorithm used in kind of typical early search engine work, where we have a graph with many vertices, and we have a value for each vertex that's representing some notion of the importance of that vertex in the graph. So this vertex in the middle, we're starting out with everything 10, and we'd like that vertex probably to get a higher value because of all of the incoming links it has. So the way we implement PageRank is we would pick the node we're updating, go through all of the neighbors, sum up the contributions coming from that neighbor, splitting the contribution of this one 2 ways between the left outgoing link and the right outgoing link, and then we'd update the value. So we're going from 10 to a larger number. And in practice, we iterate many times over, and the system converges. And there's some more details about scaling values and other things, but this is the core of the algorithm. And the challenge we found as we were building this is there's a huge imbalance between the number of links going into each of the vertices if we think about something like a social network graph. We can have some vertices with millions of links going into them, maybe billions. We can have many, many links, many vertices with only a handful of links. So we've got, on one hand, a workload that should scale very well on this kind of hardware, because we can split this work across all of those 4,000 threads and keep all of them busy working over that 16 terabytes of storage in the machine's memory. But on the other hand, we've got this challenge that we need to distribute this very erratic style of workload, because we don't want to have some of the threads run idle while other threads are kind of swamped, still processing their billion edge vertex. Now, this is a classical trade-off. Now, one end, we can divide the vertices into large batches and give each of the hardware threads a fixed batch of work to do. And that's great because we don't spend much time distributing the work, but it's bad because we have load imbalance, because threads get different amounts of scanning work to do. On the other hand, we could divide the work into very small batches and have threads kind of iteratively claim a little bit more work whenever they need it. And this is great because we get good load balance, because a thread that becomes idle can pick more work up out of neighboring threads that have got excess. But it's really bad because we've also got all of this extra work spent distributing the work. So we're kind of spending all our time managing the work and proportionally less time actually doing useful work. So typically this would be a choice where we have to choose kind of by intuition or experience where to go here, what the batch size ought to be. And the technique that we worked on at Oracle Labs was how to make it practical by knowing the hardware structure of the machine to operate at this extreme point and divide small batches of work and make that efficient. So we could forget about this manual tuning step that was needed and give more robust behavior across a range of settings. I'll quickly talk about what we do here, but effectively we've got that same idea again of knowing the physical structure of the machine and the algorithm we want, and then thinking about how we can reduce the amount of communication and make sure that the work we're doing maps well onto the structure of that physical machine. So to fit on the slide, I'm just going to show 8 sockets instead of all 16, and we're going to have 16 cores per socket instead of 32 to make things fit together. So we start out by taking the graph vertices we want and doing a kind of speculative distribution of them between all of the cores in the machine. So first core gets the first fraction of all of the vertices, second core gets the second fraction. And when I say this is a speculative distribution, what I mean is that we're not committing this core to running only this chunk of the work. We're just saying that that core is where we store the information about which of those 125-odd vertices have yet been processed. So we're spreading that metadata out across all of the machine, trying to avoid forming any hotspots within the communication fabric in the machine. Then we can also exploit the fact we have 8 hardware threads per core. And these hardware threads share a common last level cache, or they share, in fact, I think in this machine, the L1 cache. And this means that the threads that are local in the same core can communicate very efficiently, even though it's going to be very slow with a speed of light propagation delay to communicate from one socket to a socket at the other end of the machine. So we can communicate very, very quickly between the threads running in the same core. And what this lets us do is to try to combine together requests for work when a thread is getting close to the end of its own work. So we would maybe give each thread 10 vertices at a time. It would run its processing for 5 of those vertices. And when it gets to that halfway point, it would set a flag saying, I'm nearly done with my work, I need some more. So multiple threads would be running on the core. They'd all be setting these flags, saying that they're going to need some more work soon. And then whichever of the threads gets to the point where it needs the work kind of urgently, it's completely finished its own work, it then goes through the more complex path of fetching work on behalf of all of the neighbors. So we've got 3 threads coming towards the end. 1 thread gets there first and claims 3 batches of work, which it distributes out to its neighbors. So what we're doing here, we're communicating as quickly as possible inside the core. We're reducing the amount of communication that has to go through the slower, more distant interconnect. And we're also getting some overlap by letting threads signal they're running out of work before it becomes urgent. So this technique proved to be effective for these kind of large parallel in-memory machines. And it let us get some benchmark results that illustrated the potential of those systems versus some of the other multiprocessor systems and different graph analytics workloads that were available at that point. So go on a few more years, and this is kind of closer to where we are at the moment now, where instead of just having big machines be large physical machines, rack-sized systems the size of a person, we're now increasingly thinking about systems which are built over many individual machines communicating more tightly. So this could be a cloud environment where a workload is built over many 2-processor socket machines, each still with some multi-threading and some multi-core capabilities internally, but individually smaller machines. We've maybe got changes in the networking model here. This could be including remote memory access from one machine to another. So it's this kind of interesting hybrid mix where it's got some of the characteristics of a single machine, because we're programming this all together, and we're probably not wanting to handle the workload keeping running and the failure of one machine. So it's not quite like the classical distributed systems that I talk about for folk who are doing that in the lectures I was covering in 1B this year. We've got kind of some of these kind of hybrid aspects. And we've got RDMA often with reliable communication between the machines, so a kind of odd shift from where we were a few decades ago. But the challenge here is that now we do have multiple independent machines, potentially running multiple copies of the Java virtual machine or other language runtimes, all of them proceeding independently with their own work. Maybe allocating memory individually on that machine, triggering garbage collection, tidying up their heap, then restarting after the garbage collector has finished. And a challenge we noticed here when we looked at systems running was that those garbage collection pauses would get staggered out over time. What I've got on the graph here is that same PageRank workload, but now running over a set of 8 machines. And we're plotting some metrics we got out of those machines, showing them allocating space in the heap in Java. Then the heap gets almost full, and it triggers some garbage collection, which then brings the heap space down, and we go up again. And you can kind of see there's some places where we've got plateaus in this graph, where one of the machines is getting stalled because it's waiting to communicate with another machine in this cluster. But it can't get a response from that other machine because its other machine is stopped doing garbage collection and is not going to respond until the GC has finished. And so we get this a kind of loss of efficiency. We would like to be able to scale up as we add more machines, but the more we add, the more likely it is that there's some garbage collecting going on somewhere in the system, and we end up stalled behind that other machine. So it's actually a very similar kind of problem to the one that we were addressing with the linked list design to avoid using locks. Just like if we use locks, a thread would get stalled while waiting for the lock holder to finish. Here, a thread is getting stalled when it's trying to communicate with someone else who's stuck doing garbage collection at that instant. Now, the way we realized we could improve this situation was to exploit the fast communication between the machines and have them exchange information about the state of their heap and about the choices the garbage collector was going to make. So instead of having each machine individually come to a decision about whether to garbage collect or not, we would have all of the machines say, okay, one of us needs to garbage collect. We'll stop everyone at this point. We'll all do our garbage collecting at the same time, and then we'll start everyone again. So by coordinating this garbage collection pauses and lining them up, we're able to get a reduction because everyone is kind of either doing their useful work or doing their garbage collecting at the same time. And we could improve upon the overall performance of the system, potentially getting bigger improvements if we were to scale up to a larger number of nodes here. So in the last example, I'll go to some of the work we've been doing just in the last couple of years. And this is going now to looking at systems with GPUs as well as CPUs, and going to machine learning workloads, which, of course, are a huge commercial importance at the moment and underpin so many emerging services. Now, if we think about what's happening on a GPU-based system when we're running a generative language model, it's actually something which kind of surprised me when I dug into the details for the first time. So I'm not sure if the text comes up clear enough at the back, but the input here is asking the language model to tell me a rhyming poem about a tortoise and a friendly dinosaur. Now, this is an example we use internally when testing out different models, because if we damage something in the computation, maybe we stop getting valid English text at all. Maybe we get a visibly degraded response. The poem stops rhyming, is something we literally see at times. So we take the user's input, some text. We do a cache lookup in a structure called a KV cache within the implementation to see if there's a prefix of this we've seen before. So maybe somebody asked for a rhyming poem about something else. We've got a prefix matches. And then we've got a tail that we're seeing for the first time. So maybe the last half of this prompt is new. And given that, what we do is then a first round of compute called prompt processing, or sometimes prefill. And this means we are going through all of the model weights, which could be billions of values for a large model. And we're doing matrix multiply operations, other operations, to process this tail part of the input prompt that we've got. So this would be running typically on GPUs, on a cluster of GPUs. Now, what we get at the end of that large amount of processing, we get to update the cache, because now we've kind of seen this extra prefix, and we get just one token of output. So we do a whole bunch of processing, we get one token of output. And a token here might be a simple word or a couple of characters, maybe even just one character, if it's just depending on the exact way that the language maps into this internal format. And then, because we're wanting to get a kind of complete poem out here, we have to go through this whole step again and again and again. So every single token we generate, we have to load all of the model weights from the GPU's memory into the GPU for compute. We take this small piece of input, this last token and the bigger cache we're building up, and we generate one more token, and then we go around again and again and again. And so this compute cycle is one of the reasons that if you interact with language models, you'll often see it almost looking like somebody is typing, is because we are often going to be generating token by token the output, and we need the previous token we've generated in order to generate the next token. And so we get some pretty plausible output here. Now, one of the challenges in making this efficient is that we're spending, we've got these kind of two different operating modes for the system. We've got this very compute-intensive mode where we're processing hundreds, thousands of tokens together to think about the input prompt we've been given. And then we've got this, so this is kind of like a throughput-oriented job. We care about the number of tokens per second that we can pre-fill with the GPUs we have available. And then we have this kind of more latency-sensitive job where we're generating one token at a time without very much compute going on, because we're just taking one new token as input and doing the processing on that. But we're still needing to load all of the model weights and doing these computations which are stressing things like the link from the memory in the GPU into the compute. And we've often also got communication between a cluster of GPUs, where in this compute-intensive phase, we're exchanging a lot of information between the GPUs. And then in this latency-sensitive generation phase, we're exchanging much, much small pieces of information, and we want to do that here with as high bandwidth as we can, and here we want to do it with as low latency as we can. And this is some work that a group in MSR Redmond that we work closely with has developed, which uses program synthesis techniques to generate hardware-specific and workload-specific versions of these communication patterns for GPU clusters. So the topology on the right-hand side is showing the structure of the GPU cluster. We've got faster links between some pairs of nodes here. We've got what looks like some asymmetry. We've got these two links between 0 and 3, but only one link between 1 and 2. We've got some long distance links from 0 to 5. So I think if you were to look at the constraints that the hardware is designed under, this is, in some sense, an optimal way of connecting it. But it's a complex way when it comes to designing how to communicate using it. So if we think about what's happening in that latency-sensitive generation phase, we've got small pieces of information at every GPU. And the way that the algorithm works, we want to communicate those that all of the GPUs have all of the information. They need that in this particular workload to generate the next token. And the way that this synthesis algorithm works, it's able to explore a lot of alternative ways, and it can identify that the lowest latency way to communicate in this set of GPUs involves 2 communication rounds, and it gives us a performance kind of towards the left-hand side here, where we're looking at this 2-step communication with one chunk of data being communicated. And it gets us a good performance compared with the baseline system we were working with on the time. So it helps at the small case, but it's not doing well at the big case, the throughput-sensitive prompt processing part of the workload. And that's where the synthesis algorithm really provides the key benefits, because we can give it different goals for synthesis. We can say, look, try to find the lowest latency algorithm, the fewest number of rounds. Or we can give it different goals and guide it towards finding a communication pattern that provides the highest throughput. So we can see the outputs from that algorithm here as we run it with different choices. And we've got this two-step single chunk algorithm that we favor for the latency-sensitive workload. But then at some point, we switch over to a very different algorithm using multiple 7-steps communication rounds for when we're wanting to communicate large volumes of data as efficiently as possible in that initial prompt processing workload. So this gives us the flexibility to take very complex hardware like that GPU topology and in a very principled way get a algorithm that's effective for all of these different operating points we have. So I'm going to wrap up here. I've covered quite a range of computer systems now, from the single processors through to cloud and these large GPU systems that we work on today. A few common themes maybe to emphasize. The first is an attraction across many of these systems I've worked on has been how to design simple abstractions that nevertheless give good performance. So designing a linked list, one of the simplest data structures possible, while meeting the requirements of being lock-free and avoiding memory system contention where possible between operations that don't need to synchronize. Or in that distribution of vertices in PageRank across the big multiprocessor, designing that so we did not need to think about the chunk size and the distribution granularity, making it just work as we dialed down to a small chunk size, even on a large machine and a large graph. Or that last example with the GPU communication in machine learning workloads, letting the programmer just think about they want to do a communication between these GPUs and letting the synthesis algorithm identify how to organize that communication given its knowledge of the GPU interconnect topology. There's often an alignment between the hardware and the software. So I'll often be thinking about, when I do something in software, what does that cause the hardware to do? Where does data need to be communicated within the machine? What are the constraints, even down to that speed of light delay that underpins many of these examples? And how do I make sure that we're moving data as little as possible, or we're keeping data in local caches as much as possible? Also based on this experience, I kind of think about, well, what are the questions I ask when looking at performance results coming from other systems? And the amount of intricate engineering that's been needed in many of these cases means there's often a very large opportunity to improve upon the efficiency of systems. So if I start out by looking at a system that we're trying to improve, the first questions are things like, what are the bottlenecks in the system? Which resources is it fully utilizing in the machine? Is that what it ought to be using? And there can be times where you look at a system and initially find it ought to be saturating the compute, for example, but find it spending all its time fetching data from memory instead. That's often good pointers to start improving performance. There's a few very nice papers here. This idea called mechanical sympathy is another way of putting some of these notions. I think it was originally from Jackie Stewart, the racing driver, saying that in order to drive well, you don't need to understand all the internals of the engine and the motor car, but you have to understand kind of well enough how what you're doing maps onto the way that it's going to work internally. There's a great paper from John Oosterhout, a professor in the US, who gives this advice to always measure one level deeper when trying to understand performance. We ought to look not just at the thing we care about or our managers care about how well a system behaves, but we should look at things like how well is it using the caches, how well is it utilizing the compute resources in the machine. Can we really explain the high-level performance metrics that we're seeing from the system, and are we confident that we are kind of analyzing and measuring it well? Maybe there's some very straightforward ways to improve performance that come out of that measurement. And then finally, there's a very nice example from Frank McSherry, who I think was an undergraduate in Cambridge, not Churchill, who wrote this paper on scalability, but at what cost? He was looking at some large graph analytics systems and showing that actually if you implemented them very well, you could run a very large problem just on a commodity laptop by using the kind of implementation techniques that, particularly the work distribution, making that efficient, thinking about how to represent data in memory. Compared with some other systems at the time, he showed that his laptop could outperform large clusters which were not implemented with the same efficiency concerns. So let me stop at that point. Very happy to take questions as time permits, and of course chat some more over the rest of the evening. Thank you.
Thanks, Tim. Who'd like to kick off?
Thank you for the talk. I wanted to ask a question relating to the idea in the green square, simple abstractions with good performance. So I'm wondering in the context of, well, your last topic, so ML workloads, GPU systems, that's sort of related to my work area. Do you think that like the abstractions we're using for that right now, so the array programming model, these things, are the right abstractions for expressing this parallelism, distributed systems, or across GPUs, the memory hierarchies, and so on? What are your thoughts on that?
So I think things are moving so quickly. It's hard to know where they're going to be in even a year, 2 years time, which is one of the challenges, I think, of trying to define good abstractions at that field. You know, if I look at some of the work I've done in the last few years while at Microsoft, we've done a lot of innovation in the ONNX runtime system as a general purpose runtime for running a wide range of of machine learning workloads. And so that provides a good abstraction that is an effective kind of middle point between different models coming in and optimization for different hardware devices underneath. What we do see, though, is if we look online at examples like some of the implementations in a system called VLLM, or implementations for the Llama models, those models are just so important that people go right the way down to the bottom of the stack and say, okay, we'll write this using SSE instructions directly on CPUs, we'll write CUDA kernels on NVIDIA GPUs. I don't think we've got a stable abstraction that kind of lets us get quite that same level of performance yet. Now we're pushing on adding optimizations to general runtimes like ONNX, but the challenge there is just such a pace of innovation. So things like, there's a paper from colleagues at Redmond that I think it was at Redmond, certainly another the Microsoft team, I've not yet read, but they were talking about doing single bit computations in implementations. So some of these areas, the implementation techniques just change so quickly that people are still just manually coding these up and exploring them. You know, maybe at some point things will stabilize and we can figure out what the general abstractions ought to be. There are some nice things emerging. You know, one is a language called Triton for writing GPU kernels. I think also used for some CPUs and other devices. You know, that's come out of OpenAI, and Microsoft and others are collaborating on that. So it provides a more device-independent language than CUDA does for GPUs, while maybe allowing that kind of faster pace of innovation than using a target like ONNX has traditionally done. But it moves so quickly, there'll probably be more papers in the next few weeks and more ideas to explore.
Not a technical question, thanks for the talk, but there's quite a wide range of different systems, different performance things, different sizes of problem there. Is there any that you felt was more satisfying personally to work on, or to where you felt at the end of it, that was really good? Or are they all just fun?
I think, you know, all the examples here are things that I've been, I've enjoyed working on. You know, most of these have some combination of there being an actual problem we're trying to solve, and there being some performance metric where we can kind of see progress, maybe also where we can analyze the system and say, well, this is a bottleneck that we know is going to limit where we can get to, and so we're 99% of the way there. We can probably declare success at that point. Now, I didn't mention it today, but one of the related areas I enjoyed doing while I was working with with Amazon S3 in cloud storage was actually talking to customers about their performance that they were achieving with the service. There's a little screen grab earlier of, I think it's a talk on YouTube I gave when I was with S3 and giving some guidance on how customers could optimize their workloads. And there were things there that surprised people, that from this distributed cloud blob storage, you could get tens of gigabits of throughput. So many workloads that looked like they would not be a fit for distributed storage turned out with care over a lot of details, like how you do the DNS lookup, how you structure the requests, how you send the requests to the service. If you've got all of those things nicely aligned, then maybe with some variant of this mechanical sympathy idea, you could get great performance. So the contributions that were made there in a kind of unexpected way were satisfying, as well as the ones today.
Hi. I guess following on from what you were saying about, this was a lot simpler back in the early days when you could understand the whole machine and all the moving parts, right? Where one person didn't have a great deal of difficulty following what was going on. But now, when you've got a big cloud distributed system, and you need to know, like you say, about DNS and all sorts of things affect your attempt to optimize. So I'm not sure what the question is really. What do you think about this? Is it now much harder, in fact, to not waste huge amounts of computing resource because it's very hard for one person to actually understand all the pieces?
Yeah, I remember thinking back to when I started as an undergraduate. One of the things that appealed to me about computer science was I felt I could know all of the aspects of the subject, and I didn't need to pick and specialize at the time. I think we're maybe not at that stage any longer. When I look at some of the big, complicated systems, it's very difficult even to know the right questions to ask about a piece that somebody else is working on. I think that's maybe reflected in some of the examples I've talked about, where it is possible to focus on a chunk of the system, probably at the bottom of the stack. So it was necessary to think about the workload coming in, but the dependencies were a bit more constrained. Thinking about something very large with maybe dependencies on services from many different providers. I've heard many examples where it gets super difficult and people end up having a conference call with many different services present, trying to diagnose why some important customer workload is not working. I think that's super difficult.
Any more? Well, that's one of the things that struck me about computer science, that back in the early days in the 1960s, people reckoned that a third of all large projects would fail. And so we went and we designed all these tools, and we still find that a third of large projects fail. It's just that we build much bigger and better disasters these days. We've got all these tools that enable us to roll the ball a little bit further up the complexity mountain before it falls off. But of course, the business decision of what risks you take is a business decision, and the tools that you provide enable people to take different decisions. What do you think the next 5 to 10 years hold in terms of computer scientists building tools, in particular to tackle not just performance but also to tackle complexity?
I'm not sure I've got any great insights in that area. I think the approach taken in that last example I mentioned, the synthesis one, appealed to me a lot. That was using a very principled approach with the Z3 solver, enumerating the alternatives over that complex interconnect, as opposed to having heuristics or trying to use a machine learning-based approach. I guess it would be a fashionable thing these days. That came with some guarantees that the solutions that it was producing are how they relate to the optimal solution. I think that's very different to tackling project complexity, though. I've often been keen that we help with this kind of always measure one level deeper aspect in providing clearer telemetry of the behavior of different parts of the system. So maybe when things are not performing well, it's clearer early on where there might be something that doesn't line up with the way that it was designed. So that maybe gives some way to more reactively identify where there's issues. When it comes to designing systems early on, I would have to have a good answer.
Oh, well, that's something that we'll all be working on, I'm sure, for many years to come. And as we build more and more complex systems and strive to optimize them, none of us will be out of work anytime soon. But anyway, let's thank Tim for a splendid, distinguished lecture. And those of us who are going to stay for dinner, the reception will be starting at 7. Thanks again, Tim.
Thank you.